Communicating with digital signals. Three of the flaws of analog communication discussed at the beginning of this chapter were noise, not enough bands or room for everyone to communicate, and a lack of privacy. In this section, we'll learn about some of the ways that digital communication overcomes these flaws. But first, how do you think digital signals are physically transmitted? Digital signals are transmitted physically as electrical voltage pulses along wires, and that's how Morse code was originally transmitted. Electromagnetic, radio or microwaves, pulses through the air or vacuum, and light pulses through fiber optic cables. Whether signals are transmitted either over wire, through the air, or through a fiber optic cable, they are susceptible to noise. Noise can be caused by signals from other sources. For example, electrical appliances, lightning, or other radiation sources. There's no easy way to remove noise from analog signals. For example, here's your pure signal being transmitted, and then when it gets to the other end, the various types of noise distort what the picture looks like. Now, the same thing would happen to a digital signal. Okay, here's the one transmitted. Look how pretty that is, nice and neat. Then after it goes through noise, it has all this stuff. Okay, so it looks messy. However, you can still say that this is going to be a 1, this is going to be a 0, this will be a 1, because that's the closest it's to. So that's pretty obvious. This can only be interpreted as a 1. A 0 would be all the way down here. So you'll get a lot of noise, but it's still easy to take out the original signal. So let me just erase this so you can see. It's still quite noisy, but you can clearly recognize what a 1 and a 0 are. So it appears that digital signals are a lot easier to get rid of the noise and figure out what the original signal was. That's great. Let's look at the next big challenge for analog signals. You have a limited number of bands or channels on which to transmit. This really limits the number of simultaneous communications that can take place. That can be solved in 4 different ways: bandwidth, multiplexing, routing, and compression. Let's talk about how we can increase bandwidth. Analog and digital signals can be transmitted through a variety of media. When it comes to long-distance communication, the 2 main kinds of media are copper wire, right here, and fiber optic cable. Used to be microwave towers, but they've been taking them down as more fiber has been deployed. Early telephone service consisted of analog signals transmitted over pairs of copper wires. One call required 1 pair of wires. The cables between telephone switching stations could have more than 1,000 pairs. They were very large and very heavy. Digital technology enabled many calls, data, and eventually the internet to use these copper cables. Copper had many drawbacks. Heavy, it's expensive, and it doesn't carry as much traffic as you'd like. Back in the 1840s, in France, Caledon and Babinets demonstrated that light could be guided in a liquid stream. It took until the 20th century to start using glass tubes or fibers, very pure glass tubes and fibers, to transmit images and other analog and digital signals. The first installation of fiber optic cable for communication was in Torino, Italy in 1977. Now these fiber optic cables are the backbone of most communications and the internet. Also, homes connect to their providers via fiber cables in some places, or in a lot of places. And the key thing here, the light is inside the glass, and it gets totally internally reflected inside the glass, so it doesn't leave, and it can travel large distances and carry a lot of information. Let's do a quick comparison of copper to fiber. Digital signals over a single fiber cable enable vastly greater amounts of information and voice to be transmitted than analog signals. So let's say we have a pair of copper wires. We can transmit a signal 2.5 kilometers. Then, of course, we would have to amplify it to go another 2.5 kilometers, right? Because we have to get traffic around the world, cross-country. The bandwidth, well, there's no bits here. It's just measured in waves. And let's say we can have one voice channel on this pair of copper cables. What if we go digital over that copper? we can then have a bandwidth of 1.5 million bits per second and carry 24 voice channels, which means 24 conversations. Let's put it over fiber. We now have a distance of 200 kilometers before you have to regenerate the signal, 2.5 billion bits per second, and 32,000 voice channels. And fiber optic bandwidths continue to increase. The current record in 2020 is 39 petabits. That's 1 times 10 to the 15th bits times 39 per second. And it was sent 76.6 kilometers over a single fiber. But this was done in lab conditions, okay? So we haven't deployed that yet. But holy cow, right? Greater than 32,000 voice channels. Another improvement is that digital signals can carry much more information, whether on copper or fiber, than analog. Part of the reason is multiplexing, right here. Multiplexing is a method by which multiple analog or digital signals are combined into one signal over a channel. There's a special kind of multiplexing, time division multiplexing, frequently just said TDM, of digital signals enables many more simultaneous communications to take place on one channel. So in other words, in just having one call, you can have many on the same channel. Let's try and explain time division multiplexing. First, let's compare a phone call with a CD, compact disc. Sound is digitized for compact discs. The sound is converted to a 2-byte number, remember byte? It's 8 bits, at 44 kilohertz. This means that CD quality sound requires 44,000 samples per second, right? That's the kilohertz right there. That's the frequency, times 2 bytes per sample. So we get 88,000 bytes per second, or 88 kilobytes per second. Now let's talk about a phone call. Phone calls don't require the kind of sound quality that a CD produces. When you're listening to music, you want to hear every note. Voice is a lot more forgiving. Phone calls will only sample sound into 1 byte packets at 8 kilohertz. And right, that's 8,000 samples per second. That's still pretty amazing. So how many bytes per second do we need? Well, for a telephone quality sound, we have the 8,000 samples per second, right? That's the 8 kilohertz, times 1 byte will give you 8,000 bytes per second, or 8 kilobytes, right? A kilo is 1,000. 8 kilobytes per second times 8 bits per byte, and we get 64 kilobits per second, which is also known as a DS0 in telecom parlance. What TDM does is it sequences groups of just a few bits or bytes from each individual input stream, or phone call or internet message, one after the other, and in such a way they can be associated with the appropriate receiver. If this is done fast enough, the receiving devices will not detect that some of the circuit time was used to communicate with other receiving devices. So what we have here, we have a thing called a multiplexer and a demultiplexer. A person is talking over here on conversation A, another person on conversation B, and maybe a computer is sending messages on conversation C. What the multiplexer does is select each one, takes a few bits, moves on to the next one, then it moves on to the next one. At the other end, these two guys are in sync with each other. This will then break out that long stream of bits, which has added all these guys together, and send conversation A to the person who wanted to talk to person, conversation A. This goes to conversation B person, and this goes to another computer. So hopefully this explains a little bit why so many 64 kilobit per second phone calls are carried on a single fiber. Each one of these is 64 kilobits per second. Summarizing from the last slide, because this is pretty critical here, what TDM does is it sequences groups of a few bits or bytes from each individual call or computer message, one after the other, and in such a way that when they get to the other end, you have a piece of machinery called the demultiplexer that separates them out and sends the right call to the right person or the right computer message to another computer. Now, how does it get there? We talked about this end over here and this end. This piece here is routing. We have a message with an address or a phone call with an address, and every point that it goes to be regenerated or to get onto another facility carries that address to get it to the right place. That is called routing. This indicates there are many different paths. Okay, so what if this path, there were a lot of calls on it, they had no more room? The next call would go here. It would go a different way. Or what if this path, let's say it was fiber in the ground and somebody dug a hole and cut the fiber? It would automatically switch to a different path. There are many, many different kinds of routing, but one thing they have in common, they attempt to deliver their data or voice calls using the most efficient path. All right, how else can digital technology be used to transmit more information or store more information? Data compression. It reduces the number of bits needed to adequately represent the original information, whether it's music, a voice call, images, or videos. It is based on Shannon. Remember we talked about him earlier? His information theory. There are many different algorithms, which is just a fancy name for computer programs that compress data. Perhaps you've seen GIF files, JPEG for images, MPEG-3 or MP3 for music, MPEG-4 or MP4 for video and audio. I can never figure out if it's GIF or GIF, but GIF. Privacy is another concern. With analog radio transmissions, it seemed impossible until Hedy Lamarr, who was an actress famous during the World War II era, invented the idea of frequency hopping, which is just so cool. Just because you're in one job doesn't mean you can't do something else. Frequency hopping. That's when radio signals are transmitted on rapidly changing channels where the frequency keeps changing, and the order of those channels is only known to the sender and receiver. This doesn't encrypt, and encrypt means you apply a secret code to the transmission, but it hid the messages by making them difficult to find and follow. So you could pick up a piece of the message, but as you're trying to listen for more, it shifts frequency, and if you have a receiver tuned to that one frequency, you have to change it again, and it just happens too fast for you to be able to do it. So that's used for modern mobile phone, Wi-Fi, and Bluetooth technologies. Okay, hiding the signals is great, but perhaps someone does know your frequency list or has the same type of equipment. So now that information just comes over there and that can be totally read or viewed. That's where encryption comes in. The information is translated to something else using a secret code. Ideally, only the sender and the receiver have the cipher or code book. If the other person has it who shouldn't get it, well, he'll see the messages too, so you have to protect that. And they don't really use code books. This is also inside your computer programmers and transmitters and receivers. There's evidence that this idea has been around since Mesopotamian times, 3,500 years ago. So that's when we think it was started. Now, the methods for breaking codes started with Arab mathematician Al-Kindi around 800 AD. Perhaps the simplest form of encryption is something you did when you were a kid. It's called the substitution cipher. The alphabet is mapped to another arrangement of the alphabet or other symbols. So the top line here is our alphabet, and when you want to code something or decode, well, let's see, if you code, I want to say, what do I replace the letter G with? I replace it with the letter E. And if you have a message in code like this, you start on the second line. So let's do the first one. You have a Z here, so you find the Z, and that matches up with the C. So the first letter of this is C. So please try this. It's a little bit of fun, and go to the next slide for the answer. It works out to be codes are fun. Ciphers became rapidly more complex during World War II. They were so sophisticated that cryptology, the science of codes and breaking them, reached critical importance. Alan Turing from Great Britain, we talked about him earlier in this chapter. His efforts during that time advanced cryptographic methods and gave rise to the modern computer. You needed that to encrypt and decrypt messages as well as break other codes. Today there are many, many methods of encrypting information as well as breaking the codes. You might know some of them today, such as HTTPS, which keeps your internet communications private. Hopefully it's easy to understand why we need encryption today. It keeps our personal information private, plus financial information, unless we want to share that with others. This could make sense for information based on text, alphabet, numbers, and symbols, but what about calls, photos, or videos? That's where digital signals are very important. Earlier, we talked about replacing audio and images with strings of binary numbers or bytes. Each value of a byte in a byte can be thought of as a character. As we just learned, we can substitute one character for another using a cipher. If you do this, and the audio or image transmitted is intercepted by an eavesdropper, they won't be able to figure out how to hear or see what you sent. This diagram shows what we were talking about. Let's start with an analog signal. Let's say you're talking to somebody on the phone and it's a very secret conversation. Well, as they all should be, right? Nobody else's business. First thing that's done is we sample the analog signal and turn it into a digital signal. Analog to digital conversion. And here's our bits right down here, okay? 00, 11, 00, etc. Then we encrypt it. See how it's changed? Different sequence of numbers. Then we compress it so we can fit more of them in our transmission facilities, and we put an address on it so we know where we want it to go. It then comes down here to a multiplexer, and this will be conversation B. Conversations A, C, D, E, and all the others are different phone calls or different data transmissions. So our multiplexer takes turns selecting each conversation and sends it over fiber, sends it over copper, sends it through the air, whatever. At the other end, a demultiplexer separates the signals out again and sends it, and in this case we're just doing conversation B and it has an address, sends it on this path where it is decompressed, and once again we get our coded signal. It then is decrypted. So this is the actual thing we said in digital form. It is then converted from digital back to analog, and here's the sine waves again. So a person listening over there hears exactly what you said.